Hello, and thanks for tuning in to watch our talk on matrices of optimal tree depth and row-invariant parameterized algorithm for integer programming. So the aim of this short talk is to hopefully convince you all of the merits of a matroid approach to integer programming, and to also present you a new result of ours that applies these techniques to create a row-invariant fixed parameter tractable algorithm for integer programming. So before I begin, let me just say that this is joint work with Tim Chan, myself, Jacob Cooper, Martin Koutecký, Daniel Král, and Kristýna Pekárková. And you can find our respective affiliations below. We'll start with a simple question. Suppose a man on the street walks up to you and demands that you solve for x the matrix equation ax equals b for some fixed vector b. And suppose that x and b take integer values. But you get a choice of two matrices for A. You can either solve the left matrix, or you can solve for the right matrix. Now, you probably choose the rightmost matrix because it contains a lot of zeros. It looks like an easier matrix to deal with. So the first reason I mention this is because the constraints of an integer program can be represented as such an equation, ax equals b. In fact, we call A the constraint matrix, where the columns correspond to the variables of our constraints, and the entries in the matrix correspond to the coefficients of the constraints. Now, the more philosophical point that I want to make is that knowing something about the amount of zeros, or the position of the zeros, transformed what is at least a tricky problem for people into something a bit easier. So this informally is the idea behind something called fixed parameter tractability. So this is where you take a hard problem, like integer programming, but in addition to your input, you have a constant parameter that provides you some extra information about the input. And the hope is that for a fixed value of this parameter, you achieve a runtime that is polynomial. So we'll talk a bit more about this in the next slide. I also want to remark that this simplicity regarding the position and the amount of zeros in the matrix can actually be quantified by a graph theoretic notion called tree depth. And again, we're going to be talking about tree depth in the upcoming slides. So just a couple of words on integer programming. In its general form, we want to minimize some linear objective function f over all x satisfying a set of linear constraints, which we represent as the matrix equation ax equals b. But the important thing is that the entries in x are integers. Of course, this is actually what distinguishes integer programming from linear programming. But unlike linear programming, which is polytime solvable, integer programming is well known to be NP hard. In fact, it's still NP hard even when the variables in x are restricted to 0 or 1. This is actually one of ICALP-A's classic 21 NP complete problems. So in light of the hardness of integer programming, a lot of research has been devoted to finding fixed parameter tractable algorithms that use as parameters some structural measure of the constraint matrix. So first things first, what exactly is a fixed parameter tractable algorithm? So a fixed parameter tractable algorithm, or FPT algorithm for short, is an algorithm whose runtime can essentially be split into two parts. So it needs to be polynomial in the size n of its input, but it can be multiplied by a function of some parameter p. And this function can be essentially anything you like. It can be exponential, anything you want. But the important thing is that it's independent of the size of the input. And to reinforce something I said earlier, when you fix a value of p, notice that you get something that is polynomial in the input. And of course, you can have multiple parameters. You don't need to, doesn't need to be parameterized by a single parameter. So this line of research culminated recently with the following theorem of Koutecký, Levin, and on. They showed that integer programming is fixed parameter tractable when parameterized by entry complexity and tree depth. Now, this theorem was essentially the starting point of our research. And I won't define what entry complexity is for this talk, won't be necessary. I will now talk about tree depth in the next few slides. Before defining tree depth, we need a few definitions. So first of all, fix your favorite rooted tree T, since it's my favorite tree apparently. The depth of my rooted tree is simply the largest number of edges on a root to leaf path in T. So for example, in this tree, the depth will be 3, as evidenced by this path here. And the closure of T is obtained by adding every vertex edges to its ancestors without creating multi-edges. So in this diagram, red edges represent the additional edges gained from the closure operation. Moving on, given a constraint matrix A, we define the dual graph as follows. What we do is we associate each row of A with a unique vertex and join 2 vertices I and J with an edge if there is a column in A whose entries in row I and J are simultaneously non-zero. So this is best illustrated by example. We have an example below. Here is my constraint matrix. Notice it has 5 rows, so I have 5 vertices in my dual graph. And I have an edge between vertex R1 and R2. This vertex corresponds to row 1, and this vertex corresponds to row 2. The reason there is an edge there is because if I look at column 1, for instance, and I look at the entries of column 1 in row 1 and row 2, these are simultaneously non-zero. Analogously, there is no edge between vertex R5 and R2, because when I look at row 2 and row 5, there is no column that simultaneously has non-zero values in those rows. Good. So now we're equipped with these definitions, we can define the dual tree depth of a constraint matrix A. This is the smallest depth over all rooted trees whose closure contains the dual graph of A. So in the example below, I have a tree of depth 3, represented by the black edges, whose closure contains the left graph. So the left graph in this diagram is represented by the blue highlighted edges. And this shows that the tree depth of the leftmost graph is at most 3. Because this black tree has depth 3. So now I've gone to the trouble of defining tree depth, I'm going to highlight its main drawback as a parameter for integer programming. So below we have our matrices from earlier, and underneath those we have their respective dual graphs. Now take it from me that the dual graph, the dual tree depth of this dual graph is 4. But the rightmost graph actually has smaller tree depth. It actually has tree depth 2. So here's a tree whose closure contains this graph as a subgraph. But we can't do any better than this tree because this graph contains a triangle. So the tree depth of this graph is actually 2. So in particular, the rightmost graph has smaller tree depth than the left, which you'd probably expect given that its associated constraint matrix has a lot more zeros. But now I tell you that these matrices are actually row equivalent. That is, there exists a series of row transformations from one matrix to the other. So what this example above shows is that tree depth is not invariant under row transformation. That is, the drawback of tree depth as a parameter is that it really only cares about the representation of the constraint matrix, rather than the underlying geometric structure of the problem. Indeed, I can have 2 instances of IP which are row equivalent, these examples above, for instance, where the algorithm of Koutecký, Levin, and On would work much faster on one than the other. So it would work much faster on this instance of the IP than this instance, even though these matrices essentially represent the same set of constraints. So our goal was to overcome this obstacle. We wanted to know, is integer programming fixed parameter tractable with respect to some row-invariant structural measure of the constraint matrix? So this is where the matroid theory actually comes into play. So, quick recap on some matroid basics. A matroid is simply a set X together with a collection I of subsets of X. And these subsets we call independent. And this collection I has to satisfy a couple of rules. Firstly, it's got to be what's known as hereditary, which means that for any set in I, all of its subsets must also appear in I. And it must also satisfy the augmentation axiom. This means that if I pick any two sets in I, where one is bigger than the other, say B is bigger than A, then I can find a matroid element in B that's not in A, and I can put it in A, and the result is a set in my collection I. So let's have a look at a few examples of matroids, just to make this a bit clearer in our heads. We have vector matroids, for example. These are matroids where X is a finite set of vectors, and I contains subsets of linearly independent vectors in X. We also have graphic matroids, where X is the set of edges of a graph G, and I is the set of all acyclic subsets of edges in G. So it's reasonably easy to see that both of these examples satisfy the hereditary property and augmentation axiom. So now we've been refreshed on matroids, we can finally start talking about a matroid parameter called branch depth. And we'll see that this actually overcomes the main drawback of tree depth that we encountered earlier for integer programming. First things first, let's define the rank of a set X prime in a matroid M. The rank of a set X prime is equal to the largest independent set contained in X prime. Okay, so this is quite an easy definition. Now we come to what is probably the most complex definition to digest in the talk. But it's the central object from which we'll derive the branch depth of a matroid. So it's quite important. So a depth decomposition of a matroid M is a rooted tree T together with a mapping F that maps the elements of my matroid in X to the leaves of T in a many-to-one fashion. So that is multiple elements of my matroid may be assigned to the same leaf. And this mapping has to satisfy an additional property. So for every subset X prime of matroid elements, the subtree induced by X prime in T, so that's the subtree of T whose leaves are essentially the image of f of X prime, this subtree needs to contain at least as many edges as the rank of X prime. So this is a complex definition, and it's not even clear from this definition that every matroid even has a depth decomposition. But let's have a look at an example. So let's consider the following matroid X, following vector matroid X rather, with the following ground set. And to the right, I have a rooted path of length 4. This is going to be my T in my depth decomposition. And I'm assigning all matroid elements, so these vectors here, to the only leaf in T. This assignment, I assign them to this leaf here, and this assignment I'm going to call my F in my depth decomposition. So now we need to check that the rank inequality, that's this last point here, now we need to check that the rank equality holds for all X prime. So firstly note that X has rank equal to 4, and therefore all subsets X prime of X have rank at most 4. But also notice that the tree induced by each X prime is actually T itself. There's only one subtree with this guy as the leaf. Note that T contains 4 edges, and hence the rank inequality is satisfied for every X prime. in fact, this construction shows that any matroid has a depth decomposition of depth at most the rank of its ground set. So we saw that having a long path in my tree was beneficial. It was quite easy to construct a depth decomposition. But what if I try and create a depth decomposition with smaller depth? So consider the following rooted tree of 2 with vectors assigned under F as is displayed in the slides. So let's have a look at the tree in the middle. The rank of the vectors assigned to the leaves of the red subtree in the middle, so this one here, is 3, and there are 3 edges in the red subtree. So the rank inequality holds. And you can actually check for the other subtrees that the rank inequality holds as well. So with this in mind, we're now equipped to define the branch depth of a matroid M. The branch depth of a matroid M is the smallest depth of rooted trees over all depth decompositions of M. Okay, so why consider branch depth at all? And how does one even obtain a matroid from an integer program? Well, it's quite simple. All you do is consider the vector matroid obtained from taking the columns of your constraint matrix A as your ground set. And this allows us to define the branch depth of a constraint matrix as the branch depth of this matroid. So the main point here is that row transformations on A don't actually change the column space of A. So in particular, the vector matroid obtained from A in the way above is actually invariant under row transformations. And if your vector matroid is invariant, then so is your branch depth. So actually, branch depth of a vector matroid is invariant under matrix row operations. So this brings us to our results. We first prove a nice characterization of branch depth of matrices in terms of their tree depth. So let's TD star A equal the minimum tree depth over all matrices that are row equivalent to A. We prove that actually the branch depth of A is equal to the tree TD star of A. And this is a key ingredient in our main result. Integer programming is actually fixed parameter tractable with respect to branch depth and entry complexity. So in the remaining time, let me give you a very quick blueprint for the proof of our main theorem. What we do is, for constraint matrix A, we obtain the vector matroid formed by its columns and apply the following result of Kardosh, Král, Liebenau, and Mach to obtain a depth decomposition that may not be optimal size, but it has small depth. It has depth at most to the branch depth of M. But then we know by our first result that there's actually a matrix A prime row equivalent to A that has equally small tree depth. And then what we do is use the result of Koutecký, Levin, and On, written below, what we encountered earlier, as a black box with A prime to show that integer programming is fixed parameter tractable with respect to branch depth and entry complexity. Lastly, we can go one step further for certain vector matroids. That is, there is a fixed parameter tractable algorithm that calculates the branch depth and constructs an optimal depth decomposition for matroids representable over finite fields and also over rationals with bounded entry complexity. So that's it for the talk. Thank you very much for listening, and I hope you enjoy the rest of the conference. Thank you very much.